Hello, my name is Laura Montserrat Alcántar Martinez from Instituto Politécnico Nacional in Mexico. The title of my work is Improving the Surface Properties and Corrosion Resistance of an APIL 5L grade B pipeline steel by applying the nitrocarburization post-oxidation process. This research focuses in enhancing the performance of pipeline steels, which are widely used in the oil and gas industry, by improving their hardness and corrosion resistance through the thermochemical surface treatment. As experimental procedures, we prepare the API 5L grade B steel specimens and subject them to nitrocarburization and under different temperatures and times, followed by the post-oxidation process. The cross-sections were analyzed by optical microscopy to observe microstructural changes and measure layers thickness. Surface microhardness profiles were obtained using the Vickers indenter. We also performed X-ray diffraction to identify the phases formed. For corrosion testings, we used a 3-electrode electrochemical cell in a synthetic fluoride and sulfide acid solution. The tests included open circuit potential measurements and linear sweep voltammetry. Open circuit potentials were recorded to 300 seconds and linear polarization measurements were performed in sweep the potential over a range of negative 0.3 to 0.3 volts versus the open circuit potential using a sweep rate of 0.1666 millivolts per second. Corrosion rates of the treated and untreated samples were determined using the tafel extrapolation method. As a result, in Figure 5 is observed that the steel sample before and after thermochemical treatment, optical microscope characterization of the layers formed after the thermochemical treatment on the steel samples while carried out, is shown in Figure 6. In this figure, a flat morphology commonly found in the steel subject to nitrocarburization is observed. Furthermore, the layer thickness tends to increase as the treatment time and temperature increased. The minimum thickness value obtained is approximately 8 microns, and the maximum is almost 50 microns as shown in Table 1. The hardness distribution in the transversal cross-section in the treated samples is shown in Figure 7. It can be observed that the hardness values of the iron nitride layers tend to increase as a function of a temperature treatment time. The X-ray diffraction spectra of surface layer after nitriding for all the treatment conditions are shown in this figure number 8. According to this analysis, the layer is mainly composed of epsilon Fe23N and Fe3O4 for the nitrocarburizate and post-oxidate samples. In addition to these phases, the XRT shows the presence of gamma Fe4N phases, for example, for the samples treated at 520 degrees. Then, in Figure now shows the variation of the open circuit potentials over the immersion time of untreated and treated APIL 5L grade B steel. It can be observed that for the nitrocarburized steel sample under different conditions, the potential becomes more positive compared to the untreated samples. the shift in the potential is evident and it's likely related to the modifications of the steel surface when exposed to the corrosive medium. The polarization curves of the nitrocarburization samples are different compared to the untreated API 5L grade B steel sample. In the former, the polarization curves in the anodic response, it can be observed lower corrosion currents when they are polarized. Meanwhile, for the later, an increase in the current of evident as the potential becomes more positive, and it's related with the an oxidation process of the steel and the likely formation of iron oxides. On the other hand, in the cathodic region, the current remains constant in a potential range due to a diffusion control of the reduction reaction. These results demonstrate that the nitrocarburization and oxidation treatments improve the corrosion resistance of the carbon steels due to the formation of this layer acting as a barrier that hinders the entry of the electrolyte, decreasing the dissolution of the metal and the corrosion rate. In the contrary, in the formation of coupling of this layer is not uniform. This can facilitate the ingress of the corrosive medium and the oxidation of the steels. It would be case with the samples treated at 580 degrees and 480 minutes. The calculated parameters shown in Table 2, such as polarization resistance and corrosion density, result in decrease of to the 20 times less in the corrosion rate for samples nitrated at 520 degrees. As a conclusion of this investigation, nitrocarburizing post-oxidation improves both mechanical and corrosion resistance. The best condition of temperature and nitride treatment for more corrosion resistance is 120 degrees due to the formation of the gamma Fe4N phase in the compound layer. In addition, at 580 degrees corrosion rate also decreases, even though in the compound layer the gamma Fe4N phase is not formed. The nitrocarburization post-oxidation process is potential for extended service life of pipeline. In summary, the nitrocarburization post-oxidation process significantly improves both hardness and corrosion resistance, showing a strong potential of extending the service life of pipelines. Thank you for your attention.